Hi kids. Today we are going to learn an integration technique. So remember, you should have kind of two lists. You should have a list of rules, like your power up rule, your power of -1 rule, your trig rules, your inverse trig rules, your exponential rules, and then you should have another list of integration techniques. And the first technique on that list was U substitution. And the second one is integration by parts, or IBP. It is a little bit of a dagger because it is another way to try to remember how to attack an integral. Remember, when you were doing U substitution, your goal was to rewrite your integral in terms of U and du, right? That was the goal of U substitution. Well, integration by parts, the goal is also to rewrite your integrand, but in terms of not U and du, oddly, but U and dv. Say what? Crazy, right? Okay, so again, it is a little bit of a dagger because it is there is a formula associated with it. So the first thing I'm going to do is show you where the formula came from. You don't have to take notes on this because this is basically, I'm going through a proof, but this is, rather than just giving you the formula, I want to at least show you it doesn't come out of nowhere. I'm going to start with the product rules for derivatives. Because honestly, when I want to integrate a product that I can't undo with algebra or basic trig, and I can't use U substitution, I look at those things first, right? So I'm going to start with the derivative of the product rule. The derivative of a product of two functions is the first times the derivative of the second plus the second times the derivative of the first. If I call U my first function and V my second function, right? A product of U times V. I'm going to multiply this equation by dx. See what I did there? I still have equality. So if I have an equation, there's lots of things I can do with an equation. One of the things I can do is move things from side to side. So I took this positive V du and moved it over to the left. Then I just used the reflexive property of equality, right? U dv was on the right, I made it on the left, and is equal to this side. Now I integrated both sides. You see the dv was already there. I integrated both sides. What is the integral of a difference, though? The difference of the integrals. And look what happens right here. Antiderivative of a derivative. An integral with an integrand of the form U times dv can be rewritten as a product of just U and V minus the integral of V du. This is the formula you do need to write down. That is the IBP formula. It is kind of, sort of like the product rule for Antiderivatives, when you can't undo the product with algebra or trig, can't use substitution. Okay? I don't think integration by parts first when I see a product. Unlike derivatives. For derivatives, as soon as I see a product, I use the derivative rule. That's not the same here. So here are some notes to take on when IBP works well. Whatever you're going to call u, it's ideal if it differentiates down to 0, like a polynomial. Whatever we call v, dv needs to be easy to integrate because I'm going to call it dv and I want to get v by itself. If I name something dv, over here what is equal to, I have just v in both of these places. So I need to anti-differentiate this expression to get v by itself. So I need it to be easy to integrate. So again, it's kind of sort of the product rule for integration. When algebra, trig, and u substitution doesn't work. Here is a rule of thumb. This is not a mandate. This is not 100%, but this memory device, LIPID, will help you in your choice of u, because students are often uncomfortable when they have to start a problem by making a choice because they're like, oh, what if I make the wrong choice? So here's what LIPID stands for. When you have a product, right? Remember, your integrand is a product. Your integrand is a product. One of the factors, if one of the factors is logs, choose that to be u. Next, you look for inverse trig, then polynomials, then exponentials, then regular trig. Kind of weird, right? We're used to seeing polynomials and exponentials and trig, which we all kind of love doing math with those. They're down on the list of LIPID. Instead, logs and inverse trig are first. That's kind of unusual. I wonder why that is. So let's do an example. I exaggerated the fact that you have a product, right? That wouldn't normally be written that way. It would just be written like this. But that is an integral of a product. Can you get yourself out of a product by algebra? No. Can you get yourself out of a product by rewriting cosine as anything? No. Can you do u substitution? Right? What if you make cosine to the first and make u equal to cosine x? Why can't I do u substitution? Because the derivative is not in the integrand. So u substitution won't work. So since I have a product, now I think integration by parts. So I'm going to try to make this integral look like the integral of u dv. So choose u first by LIPID. Logs, inverse trig, polynomials. Who do you see first? Of the two products, here is one factor, and here's another factor. So step one, choose your u, and then really you're not choosing dv. Everybody else that you didn't choose to be u has to be your dv because you have to replace the whole integrand. None of my factors are logs, none of my factors are inverse trig, but one of my factors is a polynomial. Choose that to be your u. Take your highlighter and cover it up. Everybody else in the integrand, everybody else has to be dv. You can't leave any part of the integrand untouched. Now, so notice I worked across like in a row. Now go down. Take u and differentiate it. Take the derivative of u with respect to x and then multiply both sides by dx. Integrate dv. So take the integral of both sides. Right here, you took the derivative of both sides. Here, integrate both sides. The antiderivative of a derivative is just v, and the antiderivative of cosine x dx is positive sine x. Now, technically, it's also plus c, right? But all my constants, I'm just going to kind of carry along and then wrap them up in a big package at the end. Now comes my substitution step. I need to identify u and dv, done. And then I'm going to rewrite it I'm going to take the left side and rewrite it as the right side. So x cosine x dx, I rewrote to be u dot dv. So I can rewrite it as the product of uv minus the integral of v du. Multiply u and v minus the integral of v du. U, v minus the integral v du. But notice when I did that, my integration variables match. There's nothing to be done with this except multiplying them. Take the integral of sine, that's negative cosine. So I end up with x sine x plus, because this negative out here, negate it and you get a positive, and then I wrapped up my c here. Done. Guess what happens if you don't believe me? What can you do? Take the derivative. You got to use the product rule here, though, right? Take the derivative of this product using the product rule, the derivative of cosine, and the derivative of a constant, and I promise when you're done, you will get x cosine x. Actually, let's go ahead and verify that. Use the product rule here, the first function times the derivative of the second, plus the second function, times the derivative of x, which is just 1, plus the derivative of cosine x, which is negative sine x, and the derivative of a constant is 0. 0 goes away, positive sine x and negative sine x go away, and look at what I have. OMG. All right, let's do another one. Really, Ms. Getz? Really? You told me I wanted to use integration by parts with a product, and I don't have a product there. Yes, you do. Yes, you do. It's right there. If you really want, there. Factor 1, factor 2. Remember I told you back when I taught you the power up rule? And then when we were doing that special log, right, with u substitution in integration 5, you do not have a rule. The antiderivative of ln x is not on your list. It takes integration by parts to do. Who's your u? Think about LIPID. Right? L for logarithmic factor. That's going to be my u. Look what my dv is then. The rest, right? You have to get out your highlighter, cover up ln x, that's your u. Everybody else is your dv. Maybe you'll start to see the reason why ln x is a good choice for you, or logs are, because what happens when you take its derivative? When you take the derivative of ln or any logs, the log stuff goes away, right? Now, anti-differentiate dv, anti-differentiate 1, what do you get? X, right? To the first divided by 1, technically plus c. Now do the substitution. U times v minus the integral of v du. Make sure you know that's not ln of x squared, right? Look what happens to this integrand. X over x is just 1, isn't it? So notice I put this x in front so that no one gets confused that the x doesn't multiply the argument. And then this simplified to just the integral of 1. What's the integral of 1? X. Okay, so don't forget when you do integration by parts, you're really integrating twice. You integrate here and you integrate here. Again, if you don't believe me, take the derivative of this, and I swear you'll get ln x. What if this had been, instead of an indefinite integral, this had been definite? Right? So instead of the plus c, right? What if this had been a 1 and an e here? I would still do my integration by parts work, and I would still use the second fundamental theorem. But you'd have to plug in e everywhere, even to the part that wasn't integrated, right? It is equal to the integral of ln x. So the integral would be equal to all of this e value, not just, sometimes kids think, oh, I would just put it here. No, 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 no. The a and the b goes with everything. So plug in e here, here, and here, and then subtract, plugging in 1 here, here, and here. ln of e is 1. So this is just e minus e, which is, of course, 0, minus ln of 1 is 0. 0 times I don't care is 0. 0 minus 1 is negative 1. So I end up with 1. If you don't believe me there, go to your calculator, put ln x in y1, math 9, the integral of ln x from 1 to e. You'll get 1, I swear. I skipped example 3. We'll do that in our live session, and I'm on to example 4. Again, I recognize I have a product. I think use substitution first because I have a room. Cosecant x is inside squared, but the derivative of my u wouldn't be there. So I thought integration by parts. There's no log factor. There's no inverse trig factor. There is a polynomial factor. So I chose u to be x. dv was everybody else. Once I pick u to be x, everybody else in the integrand, everybody, has to be dv. Differentiate x, anti-differentiate v. This integral can now be written as u times v minus the integral of v du. I just floated, right? X times negative cotangent x. I just floated the negative here. Plus the antiderivative of cotangent. But that's on my list. And this was not a definite integral, so I wrap up all my constants here. Pretty sweet, right? Not too bad. Just kind of have to get used to the rhythm of what integration by parts is asking you to do. A little bit of a twist, though. This starts off just fine. A little bit of a twist on there, and I don't see it coming. I recognize I have a product, factor 1, factor 2. Using LIPID, I'm going to choose who? The polynomial, right? I'm going to choose x squared, the polynomial. I didn't have logs, I didn't have inverse trig, but I did have a polynomial. That was my u. Get out your highlighter, cover up u. Everybody else is dv. Differentiate u. Anti-differentiate dv. Use your integration by parts formula to rewrite x squared e to the x dx as u times v minus the integral of v du. Do you see the dagger now? There it is! What's true? Now I floated the 2 out. What's the dagger? Your integrand is still a product. Oh no! Integrand still a product. And I can't unproduct it with, I still check, don't forget to do this. I still look at that product and I don't think integration by parts first. I think undo with algebra trig, use U substitution, right? There's a lot of things I think, but none of them worked, so I had to do integration by parts again. So, okay, factor 1, still the polynomial, factor 2, differentiate U, and I get 1. Do you think you're going to have to use integration by parts again? What do you think the clue was? X was squared. How many rounds of integration by parts did you have to do? 2. So what if X was cubed? Ah! What if X was to the 7th? No! Look at how I made sure to keep my integration by parts in a room, because I have to multiply when I'm done with integration by parts. I have to multiply each piece by -2. Integrating e to the x is awesome. So I have x squared e to the x from the first minus 2x e to the x. This integral was just e to the x, but I had to multiply by -2, so I got positive 2 e to the x plus c. How can you check my work? Differentiate this. You need the product rule here. You need the product rule here. This, of course, would be 0. And when you were done with the product rule and taking the derivative of 2 e to the x, which, of course, is just 2 e to the x, you would get x squared e to the x. Crazy. Now, I want you to put a star next to this, because I'm going to do another twist problem, another type of twist problem. But then I'm going to come back to this idea of repeated integration by parts and handle the situation where maybe this isn't just squared. Maybe it's cubed or fourth or fifth or whatever. That would be a little bit of a dagger, so I'll show you a shortcut to doing that. But first, let me do this. So this really, it says example 1 because I would have done this in 2 days if we were in class in person, but we're combining all the integration by parts techniques into one video. So here is a product that I can't undo with algebra trig. I used LIPID, no logs, no inverse trig, no polynomials. I do have an exponential. So exponential was E, that was my choice for U. Everybody else then is dV. Differentiate e to the x is awesome. Anti-differentiate cosine x, also awesome. But look what happens when I do my substitution. What do you notice about the integrand? Just like the previous problem, I still have a product. But do you see the double dagger here? Remember what made us stop after just 2 rounds of integration by parts? It was the fact that x was squared, and when you took the derivatives, your power was going down. What's happening here, though? If I do my integration by parts again, it all works out. But look at my integrand. Still a product. Crap. All right, it's time for Algebra 1 to come to the rescue. Now, I was lazy and I didn't use my equal sign. Remember, I've just been like, well, I already know. This is what I made this u dv, and that's what lets me, by proof, say that u dv is equal to uv minus v du. So don't forget you have an equal sign, and I can see what's happening here, right? Just like Maui. You can see what's happening. This is going to just keep repeating and repeating because the derivative of e just keeps going e. The antiderivatives of sine and cosine just spin around. I'm never going to be able to unproduct that integral. So I did go through integration by parts twice. But I want you to look at what my new integrand is. Oh, no! Look at what your new integrand is, and look at the integrand you started with. Oh, snap. Right? Those are the same. How does that help? Bring the equal sign back. Doing integration by parts twice, I rewrote the integral e to the x cosine x as the same thing as what I have over here. But I want you to recall from Algebra 1, what if you had x is equal to y plus z minus x? And I asked you to collect like terms. What would you do? Add x to both sides, right? Do you see what I want you to do? I want you to take this integral, which has a negative sign, and I want you to add the integral of e to the x cosine x dx to the right side, which isn't legal unless you add the integral of e to the x cosine x dx to the left side as well. But now you have 2 of them. What was my goal? What was my goal? My goal was to integrate e to the x cosine x and tell me what it's equal to. Well, you know what it's equal to? And equal to an expression that is algebra, no integrals. Because after all, this left side is equal to this right side, but I still have an integral in it. I wanted to get rid of all my integrals. The integrals on the left and right side of an equation. Equations are so awesome. Match. So I added, got 2 of them. How do I now get this integral by itself? Hello, divide by 2. And I'm done. I have the integral of e to the x cosine x equal to an algebra expression with no integrals plus c. What? What? This is so cool. Math is so cool. Was exhausting, however. I did have to do integration by parts twice to make my integrands match, realize to bring the equal sign back, and collect like terms and divide by 2. This process was the second twist on integration by parts, right? Remember, the first one was repeated integration that stopped. This is repeated integrations, repeated and doing integration by parts when I was differentiating and when I was differentiating u and integrating dv, I had an e and a trig thing, and they kept going over and over and over. This is not, this is not common. This is down low in your bag of integration techniques, and it's like a subpart of integration by parts. But I didn't make this name, solving for the unknown integral. You did integration by parts until you got an integral that matched your original. That's solving for the unknown integral. And I did solve because I got the integral equal to an algebra expression. All right. Now I want to go back and highlight the repeated integration by parts with a polynomial factor. So I didn't have to solve for the unknown variable. This is called tabular integration. This is optional. I did not make up this word. Tabular integration is real. AP recognizes it. You don't have to use it, though. It is an optional integration by parts. It is still integration by parts, but it is a shortcut way to organize integration by parts and get the same answer when you recognize that you're going to have to do integration by parts multiple times. So it works when you have a product like integration, right? Tabular integration by parts requires that your integrand is a product. But when to use tabular is when one of your factors is a polynomial. And the other one is something that repeatedly integrates like e or trig, like sine or cosine. So I'm not going to go over these steps because this is a video. You can stop and write it down. The steps won't really make sense to you until we do a problem. So again, I'm going to go through this fast, these directions, but I'm going to talk about these directions when we're doing a problem. All right, because none of this is going to make sense. So if you would like to pause the video and write all these steps down, and then you'll have these to look at while I'm doing an example. All right, because there's a lot of words there. Or print out this screen or whatever. But you are still doing integration by parts. You're just organizing it when you realize you are going to have to repeatedly use IBP. You still use LIPID, but then you organize in a 2-column table where the left side is derivatives and the right side is integrals. So again, I'm going to go past this. And this is the example I asked you to put a star next to, right? This is what was example 5. Notice that I have 2 factors where I have a poly, which will differentiate to 0, and a repeater. Right? Anti-differentiating or differentiating, e to the x just goes nowhere, right? You just don't have any end. So I still use LIPID, and I chose x squared. I'm going to put x squared and all its derivatives in the first column. I'm going to put e to the x and all its integrals in the second column. All right, you don't have to use this notation because it doesn't matter which one's first. It's just by LIPID, you choose this, which means e to the x dx is left. So copy and paste. You take e to the x, don't change it. Then take its derivatives all the way down the column until you get to 0. copy, paste. I should have the dx here, but I'm going to cheat and not. But no, you're anti-differentiating. Anti-differentiate e to the x, you get e to the x. Anti-differentiate e to the x, you get e to the x. This antiderivative will keep going. Stop when you match the 0, right? So you need to have as many entries. That's why you do this column first. You differentiate down to 0, and then you do these antiderivatives until you have the same amount of entries. Now, starting at the top left, ignore the first entry in the second column. Put a plus sign next to x squared, which was just your original factor, and then alternate your signs. Plus, minus, plus, minus. I just didn't put the minus there because it's 0. And again, it's not really going to matter. You really don't count this one either. Now go diagonally through the column. Start top left, go diagonal down. Copy that product down. Positive x squared times e to the x. Next product, negative 2x times e to the x. Next product, 2 times e to the x, add c. If you look at the work, the notes that you did when we did this problem just by doing integration by parts twice, this is what I got. Right? Same answer. So again, this is just a way to organize repeated integration by parts as long as you don't have the solve for the unknown integral where both factors repeatedly differentiate and anti-differentiate. I was able to get to 0. Because the polynomial was squared, I only had to go through this twice. I don't know that I would bother using tabular. There is the, right? I don't know that this was that much more complicated. Notice I got the same answer. If my power is higher than 2, probably, this is easier and quicker to do with tabular, but no one will make you do tabular. So let's do this one. If you want to pause the video and do it yourself, see if you match me. But notice I have one polynomial factor that differentiates to 0 and a trig factor that anti-differentiates over and over. Sine, negative cosine, cosine, you know. Make your column, copy and paste. By LIPID, I choose the polynomial, copy it here, copy the other factor here. I should have my dx, but I don't. I usually drop it. Take your derivatives. I forgot that I wrote that. I mean, I typed it. Down the left column until you reach 0. Copy and paste sine x. Repeatedly integrate until you match the column entries in the left side. Put a plus sign next to x cubed, and then alternate your signs going down the left column. You are not going to use the last entry in the derivative column or the first entry in the integral column. Now start top left and make products diagonally through. Done. Or you could do integration by parts 3 times and get the same answer. Okay? All right, we will do some more examples like this with you in our next live session. Integration by parts. So there are 2 homework assignments, because I said this really would have been 2 lessons in our if we were live. So the first group of integration by parts problems do not use the solving for the unknown integral or repeated integration by parts that you can either just repeat on your own or use tabular, but the second group does. Okay, we'll see you next live session.